this chapter, we will be looking at how derivatives can be used to help us find extreme values. In this lesson, we will be looking at increasing and decreasing intervals. Okay, hi everybody. So in this chapter, we're going to start looking at intervals and extreme values. So we're talking about like the maximum value of a function, the minimum value of the function, stuff like that. We're going to use calculus to maximize and minimize things. And you would have done this in a previous class, but we're going to do this in a kind of much more efficient way. I guess is maybe a best way to describe it here. Now, to begin with, this is very, very definition heavy. Okay, and so the first little bit here, we're going to really just focus on understanding definitions here. Now, so to start off with here, let's take a look at what you might consider kind of a straightforward idea, but really it's not. A function is increasing if on an interval I, if for any x1, x2 in I, where x1 is less than x2, it is true that f of x1 is less than f of x2. Now, that probably doesn't mean a whole lot to you until I draw it out. And what this is saying is essentially this. Okay, let's say that I've got, here's my x1 and here's my x2. Now, because I've written it to the left of x2, I know that x1 is less than x2. A function is increasing if f of x1, okay, is less than f of x2, okay? So in other words, if f of x1 is below f of x2, and it doesn't matter what values I pick along this interval. So let's say I've got this interval out here, I'm going from there to there, okay? So here's my A, here's my B. If it doesn't matter what values of x I pick in that interval there, if I pick two of them, and x1 is less than x2, then f of x1 is less than f of x2. That means it's going up, okay? And I think that's pretty clear. What I do have to add to this, okay, is that as I go through this, you're probably, some of you, if you've gone through the course before, depending on who you've had as a teacher, you might find that what I do here is a little different than what your teacher did, okay? And the way I discuss intervals and whatnot might not jive completely with what some of your teachers have said. Others of you won't notice a difference, okay? It'll just be exactly the same to you. It's because there's a little bit of debate as to how this should be written. Okay, now I'm going to try very hard to stick really close to the definitions here. So a couple things that I need to make sure that you understand here is that when it comes to defining increasing and decreasing, you need to have 2 points. You must have 2 points. If I just drop a point right here, if I say here's my function and it's just 1 point, the discussion of increasing and decreasing is moot. It doesn't mean anything in this context. Okay? Now, you might think, and I think justifiably so, that in a calculus course, particularly when you talk about tangent lines, you might think, well, wait a minute, in calculus, we came up with the slope of a tangent at just 1 point, so why can't we talk about increasing and decreasing at just 1 point? And the thing is, when you found the slope of the tangent at a point, I mean, you found the slope of the tangent at 1 point, but you used more than 1 point to get it, okay? Even right here, there's no tangent line. If there's just 1 point, you can't draw a tangent. That's impossible. There's no defined way to draw it. What you need is a function. What I need is some sort of a function to draw the tangent line to. But as soon as you draw a function, well, what have I done there? Well, I've just drawn an infinite number of points to create this function. Because remember, a derivative is defined based on a limit. And a limit is defined using all the points on one side and the other of a given point. Now granted, we are trying to find the slope of the tangent at 1 point there, but we're using all the points in the neighborhood to help us define that. So yeah, our end result there is the slope of the tangent at 1 point, but I used all of the points on either side of that point to get there. And it's important that you catch that, okay? So you did need more than 1 point to find the slope of the tangent at a point. To come up with increasing here, I need to compare 2 points. Very important that you keep that idea in mind. Okay, so now a function is considered increasing on an interval I. Now, and by the way, I should also point out here that I didn't specify what kind of interval this was. And I've gone through and done a bunch of research. I've looked at a whole bunch of different resources here, and none of them do. The interval I is always left kind of undefined as to whether it's open or closed. And so I think you have to assume the most general, which would be that it was closed. Okay? So, any interval I here, if this is all true, it's considered increasing. Now, by the way, for those people that are a little bit more nitpicky about this, if this is true, okay, specifically this is true, that f of x1 is always less than f of x2, this is actually what we call strictly increasing. Okay? Strictly increasing. If, on the other hand, it's true that f of x1 is less than or equal to f of x2, I love what they do with this. This is considered non-decreasing. Nice way to kind of spin that. Anyway, that's okay. So let's keep going here. So a function is considered increasing on the interval I, including the endpoints. And that's what I'm trying to get at here. Including the endpoints. Because they never specified that this couldn't be an open interval, it's just an interval. I got to assume that I can include the endpoints. If, for any c in that interval, excluding the endpoints, okay, excluding the endpoints, it is true that the derivative of that function is positive. Okay, now, so what we're saying here, and if you go back to what I drew right here, notice that if you take the slope of the tangent at any point along that interval there, the slope of the tangent is going to be positive. And that's going to be true, okay, throughout that interval. Now, that's not necessarily true at the endpoints because the derivative isn't defined at the endpoints. But that's okay. That's totally okay because if you compare this endpoint to any other point in that interval, to go from there to there, it's increasing. So I can still apply that definition of increasing using the endpoint. I cannot, however, use this property at the endpoint. This property doesn't apply at the endpoints because the derivative's not defined at the endpoints. But, okay, I know that that interval would still be increasing if that interval included that endpoint. So what that means here is when you take a look at a function like this, okay, and just notice how I've written this out here. Notice that f primed of x is greater than 0, so the derivative is positive on the interval negative infinity up to c. Now you can't quite see this, but this is the value c. And then from d out to infinity. So it's increasing here. Sorry, it's all positive here, it's all positive there. That means, okay, that means that the function is increasing from negative infinity up to and including c, together with the interval from d out to infinity. Now I include the c and the d, because if you compare that point right there to any point previous to it, that's along an increasing interval. If you compare this point to any other point to the right of it, that would obey the definition for an increasing interval. Okay, so let's look at this example here. And this is an important one, and I want to make sure that this is understood well here. This is just a cubic that's been translated over here. So as a cubic, okay, the slope of the tangent right here is equal to 0. Okay, the slope of the tangent right there is equal to 0. So when I ask where is the derivative positive, okay, that's going to be positive from negative infinity up to, but not including c, okay, union c, not including c, out to infinity, because the derivative is 0 here. So the slope of the tangent line is positive on this interval. Now, but it's important to remember that that is just a tool for helping us to determine on the intervals where a function is increasing. It is not the rule that defines what increasing is. So, in other words, a function has a positive derivative because it's increasing. It's not increasing necessarily because it's got a positive derivative. And so the reason I say that is because this is now increasing on the interval negative infinity to c, inclusive, union c to infinity, which really, if I'm including those in both those parts there, it's really just increasing from on the interval negative infinity to infinity. Now, there's going to be some people that disagree with that, but if you just think about this, if you think about the interval from negative infinity to infinity, and just compare that point right there to any point to the left of it, it's above x. It's increasing here, right? So from any x value to this one, okay, where that x value is less than this one, this y value is greater than this y value. Compare that to anyone to the right of it, it's the same thing. From there to there, it's an increasing interval. You compare anything from here to here, it's increasing. At no point does it decrease, okay? In fact, if you really wanted to kind of split hairs in this one, this interval is increasing, or sorry, this is like a non-decreasing interval, or what one might even call monotonic. Okay, another word for that is monotonic. It is increasing all the way through there. Okay, that you may have picked up here that this has been an issue in the past here, trying to get some clarity on this particular issue here. If we talk about decreasing, we basically use the same sort of discussion here. A function is decreasing on an interval I, not specified whether that's open or closed. If for any x1, x2 on that interval where x1 is less than x2, it's true that f of x1 is greater than f of x2. So again, what does that look like? Well, here's x1, here's x2. x1 is less than x2 because it's to the left, and we've got some sort of interval there to there. And the function's doing this. So as long as it's always true in this interval, no matter what pair of points you pick, no matter what pair you pick, if f of x2 is below f of x1, then it's decreasing. That's the definition. Now, it just so happens that every time you do that, the slope of the tangent line is going to be negative, except at those endpoints. Because remember, the derivative is not defined at the endpoints. But that doesn't mean the endpoints don't get included here. Because I don't need to talk about the derivative at all to get that this is a decreasing interval. All I need is the definition that I just gave you. Okay, but here we go. So a function is considered decreasing on the interval I, including the endpoints, and I really want to stress that again, including the endpoints, if on that open interval, okay, excluding the endpoints, the derivative is always negative. Then again, we might consider the following example. Similar, well, it's the same example as I just gave you a few moments ago here. So here's C and here's D. So this particular graph here, notice that the derivative is negative on the open interval C to D. Okay? But if you look at the closed interval C to D and you pick any 2 points, including the endpoints, okay, it satisfies the definition for decreasing completely. So the derivative is negative on the open interval, but it implies that it's decreasing on the closed interval. So let's take a look at this example right here. So in this case, notice that the function is negative, or the derivative is negative on the intervals negative infinity to c. So here, we've got the vertical asymptote here at c. Okay? So negative infinity to c, c to infinity. And normally you would conclude that this function is decreasing on this closed interval, including c. And now I want to address this because I understand that what I've done thus far might lead you to conclude that. However, you can't include this here because in this particular case here, there's a little bit more going on. And actually, we're going to talk about this. There's a name for this. We're going to start talking about critical numbers here in a bit. The problem is it's not defined over the closed interval here. This function is only defined on these open intervals. And so you can't include that value c there. That's just because there is an asymptote there. So you have to be aware of that. There's not just one piece of information that you can kind of take in isolation. You got to consider everything, which is actually just a wonderful aspect of this here. There's all sorts of information. You got to consider it together as a unified whole to understand what the function is really doing here. So in this case right here, this would be considered decreasing over this interval here that's open. Okay, so let's take a look at now some more definitions here. The extrema, okay, so extreme values here. So a local maximum point occurs, okay, at some point c comma f of c, when f of c is greater than f of x for all x in the neighborhood of c. Okay. Now, we're being really specific here in our vocabulary here, and I hope that this makes sense. We are using the word local here in this definition. Okay. When we have a neighborhood around the point. So what I'm talking about here is if you've got a point that does this, and you draw a little neighborhood around that point here, if this has got the largest y-coordinate amongst all of the points in that neighborhood, then it's considered a local max. The important part of the local max is I can approach it from the left and the right, meaning I can use the derivative to find this. Again, I'm going to say that again. With a local max or a local min, we're going to get to that in just a second, the definition includes the neighborhood of that point, which means I'm coming at it from both sides, which means I can use the derivative to find that. Okay? So, and just right here, I've got the definition again for a neighborhood. It's defined as the set of points on a graph such that if you take the absolute value of the difference between x and c, so here's your c value, you take some point over here, as long as it's smaller than some epsilon, which would be the radius of this, it's considered inside that neighborhood. It's just inside that little circle, okay? Now a local minimum, local, again we're using the word local to imply this, is the same thing. It's just that f of c this time is less than, okay, so here's c, it's less than all other points in the neighborhood. And again, the word local, meaning I can come at it from both sides, meaning I can use the derivative to find it. The local maximum or minimum value, and this is something that should be kind of reviewed from way back when, that's just the value of f of c. Okay? It's just the y-coordinate of the maximum or the minimum there. Now, some other vocabulary here. An absolute maximum point occurs at the point c comma f of c when f of c is larger than f of x. So, and f of x being all other points on the graph, okay, in the domain of the function. So in other words, if there's a point out there that's got a larger y-coordinate than every other y-coordinate on the graph, then it's an absolute maximum point. Okay? Now, and note, there really can be only one absolute maximum point. Okay, because if you've got a whole bunch of, like for example, a sine function hasn't got an absolute maximum because there's an infinite number of them at the same height there. But that's different than the absolute maximum or minimum value. Okay, and I think we'll talk about that in just a second. Same thing for the minimum value, just on the other way around. So if you've got some point there, and I know this is a lot of writing on one page here, so I'm going to try really hard here to focus your attention. The absolute minimum point is just that point where that value of y is smallest for all of the x values in the domain. And again, there can only be one. But compare that to your absolute maximum or minimum value, which is just the value of the y-coordinate of that point. Now, you can only have one absolute maximum value, okay? But you can have, there can be an absolute maximum value even if there isn't an absolute maximum point. And I'm going to use the sine function here again as my example. The sine function's got an infinite number of points that are at the highest point, so there's no absolute max. But the absolute maximum value that it gets to is going to be 1. Okay? Now, that I think is pretty straightforward for a lot of people. I don't think I've said anything there that's a little out there. But it opens up a question to what do you do with the endpoints? And this has been a bit of an issue even as I've been teaching for a while here, because there's been some concerns that sometimes the definitions that we use we're not applying correctly. And this is why I've done this. I've kind of written this thing up here and I've approached this again because I want to be consistent with this as much as I can. So when a function is defined on on an interval closed at either or both ends, okay, and it's important. We're going to start talking about what happens when you have a closed interval. If it's an open interval, you're not including the endpoints, then there's no issue. Okay, then there is, for example, no minimum there because there's no point there. So we get these endpoints. That can be, okay, wait a second, or both ends, the endpoints of the interval be either a local maximum or a local minimum. Now, sorry, I should not have used the word local there. It can be a maximum or a minimum. The word local is not enough because it implies that there's an open interval here. So, okay, yes, but not in a strict sense of the above. So local max minima exist only within an open interval. So you can approach them from both sides. But if you're talking about an endpoint, you cannot approach the endpoint from both sides. There's going to be one side that you can't. I can only approach this point from the right. I can only approach this endpoint from the left. So this is what leaves us with these definitions here. I've got to have a left-hand maxima and minima. So if the function is defined on a closed interval a to b, and the derivative is positive for all functions along there, okay, okay, so we pick some value here for b. We've got this epsilon here as our arbitrary constant. Basically what we're saying here is that if you've got this function right here, this point right here, this is my b value, okay, this is the end point, okay, of my interval here. Here's my b value. This is a left-handed max because I can approach this point from the left-handed side here. The derivative is positive all the way up to it, and then a stop right there. That point does exist. That's a left-handed local max. You can't just call it a local max because that implies coming at it from both directions, but I can say left-handed there. And that tells me, at least I get a very clear image that that's an endpoint. Okay? On the other hand, I can do the same thing here. If a function f of x is defined on the closed interval a to b, and the derivative is negative for all x in there, then so I've got this thing dropping. So here's my b. Then this is going to be a left-handed local min. I can only approach it from the left. Now you might not even need the word local in there. If you just said left-handed minimum, that again would communicate that this is an endpoint. Same thing for on the right hand, okay? I can have a right-handed min if the only way I can approach it is from the right, or a right-handed max if the derivative is always negative there. Here's a. If I can only approach it from the right, that's a right-handed local max. Okay, and actually we're going to see how this is consistent. This idea right here is very, very consistent with Fermat's theorem. Okay, and I'm going to write that out here. I'm going to have that for you in a few minutes here. Not Fermat's last theorem. That'd be pretty cool to be talking about that. Not Fermat's last theorem, if you've heard of that, but just Fermat's theorem. Okay, very consistent with that right here. Let's just take a look now at some examples, or an example. So consider the function here shown below. So here's your function, kind of wiggles around like this. It's defined on the closed interval m to n, so we are including the endpoints. So we might even draw like a little square brackets there just to indicate that it's being included, if that helps. So what we want to do is just identify what's going on with each of these things here. So for example, a would be an absolute min. Okay? But it's also a right-handed min. Now, knowing that it's an absolute min and a right-handed min, I know that it's the left-handed endpoint, or the left endpoint of this domain. Okay, and I got a really clear image of what that looks like. Now, b is going to be a local max. I can approach it from both sides, and it's the maximum. It's not the maximum of the whole function, just in its neighborhood. C, that's a local min. I've already identified the absolute min. I can approach C from both sides, local min. D is a local max because I can approach it from both sides, but because it's got a y-coordinate that's larger than all the other y-coordinates in the whole function, this is also the absolute max. And again, knowing those are both true about that point paints a picture for me. I can see it. I know that it's not an endpoint because it's local, not a left-handed or a right-handed one. Here, E, I can approach it from both sides. This is a local min. F, okay? Now, F is just a left-handed max. It's not an absolute max. It's just a left-handed max, which tells me that it's going to be the endpoint on the right-hand side of this interval, but it's not going to be way up there or way down there. It's just kind of somewhere in the middle of the activity. Okay? So all of these words, if I didn't have the diagram here, this, just knowing the descriptions of each of those points here would actually give me a fairly good idea, roughly speaking, of what how this function is behaving. Okay? Let's take a look at some more examples here, and then what we'll do is I'll introduce to you Fermat's theorem, and we'll do some more examples going just one step beyond just these intervals. All right, let's take a look at an example here. So this question says, determine the interval where f of x equal to 2x squared minus 8x is increasing and decreasing. Okay, now what I would ideally do is have this infinite table of values, okay, where I would plug them in, I would have all of the values of x and y lined up, and then I could look at them, I could compare, I would know all of the x values are increasing as I went down my table, and then I would look at the y coordinates, but I would have all infinite of them, and I could tell you where it's going up, where it's going down. That's completely impractical. So I have a shortcut tool for this. I'm going to take the derivative. So the derivative of f will be 4x minus 8. Now, what I'm interested in is where is my derivative here positive, where is it negative? Okay, because that's going to give me an idea as the increasing and decreasing. Okay, now, so to figure that out, what I'm going to do first of all is figure out where it's equal to 0. Okay, because on one side of a 0 it'll be negative, on the other side it'll be positive. So knowing where the 0 is, that's a huge step into figuring out where the derivative is positive, where it's negative. So bring the 8 over, and I'll get that x is equal to 2. Now, here's 2 on the number line. The graph of 4x minus 8, which is my derivative, is a line that's got a positive slope, meaning it's going to look something like this as I go through. So it's going to be negative over here, and it'll be positive over here. So, just to be clear, the derivative is going to be positive on the interval 2 out to infinity. The derivative is going to be negative on the interval, negative infinity out to 2, but not inclusive. Okay? That's okay. That's totally okay. What this means, though, this implies that this function is increasing on the interval 2 inclusive out to infinity, and it's decreasing on the interval negative infinity up to and including 2. Now, doesn't that seem kind of weird? Like, how come that 2 is part of both an increasing interval and a decreasing interval? Like, what's going on at the 2? Well, that's a great question. Hold on to it. We're going to come back. I'm going to circle around to that in just a few minutes here. But now let's take a quick look at what this graph looks like. And actually, I think it's probably pretty clear for most people, because at this point here, you know that it's a quadratic, right? And the graph, and the graph looks a little something like this. Comes down, goes back up, and right here, here's your value of 2. And so you've got your vertex down here, and this is going to become my minimum. Whoops, you can't see that. This is my minimum point. More than that, this is a local min, I should have said, but more than that, this is an absolute min, because it's the lowest point on the graph. And you would have known that because it's a quadratic, and you would have had some experience with that in the past here. Okay, let's take a look at another one And then we're going to throw in another little definition here. So all right, this question we see that it's asking us to state the intervals of increase and decrease for the function 2x cubed minus 15x squared plus 24x. Okay, so before we even get there, this is a cubic. I know it's a cubic, and I probably should have actually discussed this in the previous question, but this is a cubic. It's a positive cubic, so I know it's going to have a graph that looks something like this. So I already know it's going to be increasing, then it's decreasing, then it's increasing. I don't quite know where that's going to occur, but I have enough experience with functions to know that that's what that's going to look like. And so what's going to happen here is the calculus is just going to confirm that. And once again, if I had the ability to come up with an infinite table of values, this would be really straightforward, but I don't. That's impossible. So I'm going to use my little cheat here. I'm going to use the derivative. So the derivative is going to be 6x squared minus 30x plus 24. I am interested in where this is going to be positive and where it's going to be negative because I know that will correspond to intervals of increase and decrease. Not perfectly, but just about. Okay? So to start off with, though, I'm interested in where that goes to 0 because that'll give me those boundary points where increasing and decreasing are changing. I'll divide by 6 and I get x squared minus 5x plus 4 is equal to 0. That's a quadratic that shouldn't require the quadratic formula for me to solve. So I know that I'm going to have points where this goes to 0 at 1 and 4. So I know that the derivative is changing on either side of that. So if I take a look at my number line here, here are the numbers that I just spit out here. Bear in mind that my derivative is a positive quadratic, so it's going to open up. So it's going to look like this. Now I don't really care specifically that the first derivative is a parabola. What I care about is the values of the y-coordinate that indicates. Okay, so to the left of 1, all of those y-coordinates, all of the values of the derivative are positive. In between 1 and 4, all of the values of the derivative are negative. And to the right of 4, all of the values of the derivative are positive. So, if I was to ask this, where is the derivative positive? That would be on the interval negative infinity to 1, union 4 to infinity. I don't include the 1 in the 4 because the derivative is 0 there, not greater than 0. The derivative is negative on the interval 1 to 4. But assuming that the function doesn't have any of these undefined values and any asymptotes here, I know that when the derivative is positive on an interval, on an open interval, that means that it's going to be increasing on its closed interval. So negative infinity to 1 inclusive, 4 to infinity inclusive of those values. Now, not inclusive of the negative infinity and infinity. Those aren't real numbers. You can't include those. And so now this is going to be decreasing on the closed interval 1 to 4. And again, that seems a little weird, doesn't it? That I'm including the 1 here at the end of an increasing interval and at the beginning of a decreasing interval. It's in both. And 4 is at the beginning of an increasing interval and at the end of a decreasing interval. Isn't that weird? Yeah, we're going to talk about that in just a second. That is significant. Okay. Now, I've already had discussions with some colleagues who did not like what I was doing there. But I also know that there's lots of people out there that look at this and go, well, yeah, that makes perfect sense to me. It seems to follow the definitions completely. So I'm kind of sticking to my guns on this one, that makes sense, and that there needs to be, like, you need to consider all the information here together to really see what's going on. Now, when you graph this, that graph looks like this. Goes up, down, and up here. It's just like a cubic would. And so here, this is 1, this is 4, okay? So right here, I get that 1 here is a local max, okay? And I can figure that out from here, really, and that's what I'm really going to talk about in just a couple seconds here. A local max, and this is a local min when I graph that out. But that makes sense because the 1 here, that's the endpoint of an increasing sequence, the beginning of a decreasing sequence. Now it's both, okay, it's connected to both, so I can approach it on both sides. I can use the derivative to figure that out. Here, again, 4 is the end of a decreasing sequence, the beginning of an increasing sequence. It exists on both, so I can approach it from both sides here, and it becomes this local min. Well, I tell you what, now's a great time. Let's talk about Fermat's theorem. Okay, so here we go, Fermat's theorem. Now, what we're looking at here is a little bit simpler than what you would see it in a university textbook, or if you were to look it up on Wikipedia or whatever. But this does catch the essence of it without getting into some of the notation that maybe is a little bit confusing. Basically, it just says this: if a function has a local maximum or minimum at x equals c, so you're looking at a function, it's got a maximum or minimum, you can see it right there, then it has to be the case that either the derivative at that value is 0 or the derivative does not exist. Okay? Now, we call those points here, those values of x, critical numbers of the function. Critical numbers of the function. Now, not critical numbers of the derivative, critical numbers of the function. Okay? And bear in mind, we assume the existence, I know I'm taking my time to write that, but we assume the existence of the local maximum or minimum values. It's there already. They do exist. So what's happening here is x equals c. C must be in the domain of the original function to be a critical value. It has to be in the domain of the original function to be a critical value. Okay? If it doesn't exist, if the function has an asymptote somewhere, then it doesn't exist. Okay? As a critical number. And you're going to see that pop up several times here where you're going to get asked for a critical number. Really the issue here is about where the derivative does not exist. Sometimes the reason the derivative doesn't exist is because there's an asymptote there. And that doesn't count as a critical number. You have to actually be looking at a max or a min. It must be in the domain of the function for that to work. Okay, enough said about that. But just note here that if the derivative is equal to 0, that does not automatically mean that a local maximum or minimum exists. You got to look at the flow of Fermat's theorem here. If you are looking at a maximum or a minimum, then this must be true. But it doesn't necessarily work the other way around. Okay? It does not work the other way around. Just because the derivative is 0 or undefined does not mean that you are looking at a maximum or a minimum. Now, let's take a look at some examples. All right, so this question says, find the extreme values of y equals x minus 2 squared plus 3. Okay, now we're starting with a fairly easy one here because I suspect a lot of you look at this and go, oh, well, it's a parabola. And it's a parabola that opens up. Oh, and I know that the vertex is the point 2, 3. Okay, well, there it is. It's got a minimum when x is equal to 2 and the minimum value is 3. Huh, done. Okay, yeah. I know you can do that. Let's use calculus. Okay, so that is our goal. Let's just make sure that calculus tells us the same thing. So we are now looking for, we are looking for those critical numbers that Fermat was talking about. Okay, so let's take the derivative here. So y is equal to 2, y prime, we're looking at the derivative, is equal to 2 multiplied by x minus 2 to the 1. And then the derivative of plus 3 goes to 0, so it goes away. So to find an extreme value here, if it exists, then we know that the derivative is going to equal 0 or be undefined. So I'm going to set my derivative equal to 0. Now notice this is really similar to what we were doing just a few moments ago with determining intervals. And I know that that's going to be true at x is equal to 2. Which means to me, it's in the domain of the function, okay, because the domain of the function was all reals, okay, that this is a critical number. This is a critical number or a critical value of the function. Which means critical value, it could be a max or a min. So let's take a quick look here and just see if I look at my interval here. Okay, if I look to the left of 2, I want to see what the intervals are because the intervals will give me a hint. Now, technically, I'm probably not supposed to do this until a later lesson where we look at something called the first derivative rule. But it's right here. Like we're right on top of it here. So to the left of 2, if I look at my derivative, I pick a number to the left of 2 and plug that in, my derivative becomes negative. To the right of 2, it becomes positive, which means my derivative is negative on the interval negative infinity up to 2. My derivative is positive on the interval 2 to infinity. Now, not including those endpoints here, which means that this is going to be decreasing on the interval negative infinity to 2 inclusive, increasing from 2 to infinity, okay, including the 2 here. So now I know that I'm decreasing to 2, increasing beyond that. This is a critical number, so it's a possible max or a min. Looks to me like I've got a min at x is equal to 2. Now, what that minimum value is, I don't know until I plug it in and figure that out. Now I can tell right away, though, it's 3. I knew that from the beginning. So the calculus here tends to match, it matches perfectly what your experience with quadratics is telling you. Now, when it comes to studying quadratics, this is perhaps a little bit of overkill. I mean, you didn't need to do all this. However, we increase the degree of this function by a little bit, then all of a sudden this does become the most efficient method to analyze that. Let's take a look at another example. Okay, find the extreme values of y equals x cubed. Okay, the extreme value. So we're looking for maximums and minimums. If they exist, we know that the derivative will be 0 or undefined. So let's take a quick look. So find the derivative. That's going to be 3x squared. Awesome. That's fantastic. Now, bear in mind that this function is defined everywhere. Okay, there's no break in the domain here. Let's take a look at this one. Is the derivative undefined anywhere, everywhere, or anywhere, I should say? The answer is no. It's defined everywhere. So that's not going to be an issue. The issue is where does it go to 0? And it goes to 0 at 0. Perfect. So that looks like that could be a max or a min. Now, what we want to do here is let's just take a look at the intervals here. Let's see what's going on. So at 0, okay, that's where our derivative goes to 0. That's my possible max or a min. To the left, if I plug in a number here, to the left of this, I see that I'm going to get a positive value. So this is positive on the left-hand side. On the right of 0, if I plug that into my first derivative, I'm going to get a positive value. So this means that my derivative is positive on the interval negative infinity to 0, okay, not including the 0, union 0 out to positive infinity. Okay, well, the derivative isn't negative anywhere, so it's never decreasing. But this means that it's increasing then, or maybe I should say it like this, it's non-decreasing on the interval negative infinity to positive infinity. It goes right through the 0 there because, remember, it is defined at 0, so I'm going to include it. Okay, so I would go with hard brackets on the zeros, but I might as well just go over the whole thing here. So it turns out that's not, even though the derivative went to 0 at x equals 0, that didn't correspond to a max or a min. So this is just an example of where that occurs. That rule that we read in Fermats Theorem just says that if they do exist, then the derivative must be 0 or undefined. But just because this derivative is 0 or undefined doesn't mean it is a max or a min. You need to investigate that a little bit further. So what's going on with the cubic here, if we draw that out, it actually becomes a fair bit clearer. Okay, it increases, it levels out for just a brief moment, and then increases again. Okay, that's what's going on. Okay, so now in these next two examples that I'm going to do here, all we're going to do is focus on finding the critical numbers, so the critical values of a given function here. So now I've got this function 2x cubed minus 9x squared minus 60x plus 82. So a lot going on there. Okay, but it is a cubic, and so I anticipate that a cubic should look like this, meaning I expect to get two critical numbers, because in a cubic, okay, assuming that it's doing this, the kind of the stereotypical cubic thing to do, well, there's a local max right there and a local min right there. If they exist, then the derivative must be 0 at those 2 points, or undefined at those 2 points there. Okay, or even defined at one, undefined at the other. We'll talk about that in just a little bit here. But so to start off with here, I have a bit of a sense of what's going on, so let's just see if the math kind of corroborates what I believe here. Let's take the derivative, and that is going to be 6x squared minus 18x minus 60. Okay, and I'm going to set that equal to 0 because I'm interested. Now, first of all, I should have said here, notice that the domain here, I should have gone right back to this right from the beginning here. This is always an important step. The domain here is all reals. It's just a cubic. It's just a polynomial. It's defined everywhere. Notice additionally that my derivative, the domain of my derivative is all reals as well. It's defined everywhere. So there's really no issue of the derivative being undefined. We haven't seen that yet. We will in a bit. So all I can look for here is where my derivative goes to 0 to satisfy that definition. So that leaves me with a quadratic that I got to solve. So I'll divide everything through here by 6 because I'm lazy and I prefer to work with easier numbers here. And that gives me a quadratic that I should be able to factor relatively easy. Looks like -5, +2, which means the derivative goes to 0 at -2 and +5. Those are where the derivative is 0 in the domain of the function. Those are going to be my critical numbers. Okay, and so those are going to correspond to our maxes or mins. They're going to end up being the end points of intervals of increasing and decreasing. Okay. Now, for the time being, I'm not going to focus on how to interpret that and how to graph this thing. Just suffice to say that those are the critical numbers without us doing any more investigation on that. But let's take a look at another one here. Okay, so now in this question, we read, find the critical numbers of f of x equals the absolute value of x. Okay, first of all, what does the absolute value of x look like? Okay, well, you should know, again from experience from previous classes here, that we would break up the absolute value of x into two functions here. It'll be just x if x is greater than or equal to 0, and negative x if x is, if x is, let's say, less than 0. Now, I could also have written or equal to 0. I could have made this greater than 0 and made this less than or equal to 0. The 0 gets included, okay, because the function is still defined at 0. But whether you include the 0 in one or both of those particular intervals, it really doesn't matter. We've had debates with teachers. I've watched them discuss this, and I really think at the end of the day it doesn't really matter here one way or the other. However, we know that the graph looks like this. It's got this really stereotypical V shape to it. Okay, that point right there is clearly, a min. In fact, it's the absolute min. Now, that being the case, though, let's take a look at what happens when you take the derivative of this function. Okay, and the derivative of this thing, and here's, I'm not going to go through the details of finding the derivative again with an absolute value function, but I want you to remember, hopefully you do, because this was brought up way back, close to the beginning of the course here, that the derivative is 1 so long as x is greater than 0, and it's -1 so long as x is less than 0. See, there did arise a problem at 0. And that's because you need to define the derivative in terms of limits. And you have to remember how that worked when you use first principles here. it was -1 coming this way, +1 coming this way, because the two functions were not meeting up, okay, the derivative at 0 did not exist. So this thing right here, the derivative does not exist there. Okay, so here's an example of, as a result here, since f primed at 0 does not exist, okay, doesn't exist, but x, sorry, not x, but 0 is in the domain, we know x equals 0 is a critical number, or a critical value of the function. Whoops, I'm almost off the page here. Okay, so here's an example, and this is just going to be one of many. Okay, but I use this one because we specifically looked at the absolute value function a long time ago to demonstrate that the derivative did not exist at that point. Okay, so anyway, there's we go. Now I want to look at just one more example that throws in just one extra little bit of information for you to consider. All right, so for this last example that we're going to do, it says find the absolute maximum minimum values of the function f of x is equal to 2x plus 1 squared plus 3 on the interval between -3 and 2. Okay, now I chose a parabola here because you already will have a sense of what that looks like. Okay, so you know that this is a parabola that opens up. Okay, it's going to have a vertex at -1, 3. So because it opens up, and because that -1 is in the domain here, I know that that's going to be the absolute minimum, and the absolute minimum value will be 3. Then what I would just have to do is look at the endpoints here to figure out what the absolute maximum is. So you already have a sense of that. So let's take a look at what calculus tells us to do here. So first of all, what we're going to do here is pay very close attention to the fact that that's my domain. Okay? So what I'm looking for now are critical numbers, because if a maximum or a minimum exist, the derivative will either be 0 or undefined in the domain of that function. So there's my domain. There's no issue within the domain. Okay. So first of all, where does f primed of x equal 0? Because that will be a critical number. So let's take the derivative. Bring down the 2, that's going to be 4x plus 1 times 1 plus 0. I'm going to set that equal to 0, and I'll get that x is equal to -1, which is, I knew that was going to happen. But anyway, there it is, x is equal to -1. So therefore, -1 in the domain of the function, this is right here, this is a critical number. Okay, critical number of this function. Now, I might ask, where is f primed of x undefined? Now that might seem like a bit of a silly question at this point because it's a polynomial. You think, well, it's not undefined anywhere. Oh, but it's only defined on the function -3 to 2. So I've got endpoints here, and a derivative cannot be cannot be defined at an endpoint. So therefore, I've actually got two others. -3 and 2 are both going to be, are both critical numbers because they are in the domain of the function, clearly in the domain of the function, and yet the derivative is undefined there. Not because of the function, but because of the domain that's been imposed on it. I cannot define a derivative at the values -3 and 2 because the function doesn't exist beyond those. Okay? So just so that you got that clear in your head here. So I've got 3 critical numbers here. Now, if I want to know whether these are increasing or decreasing or whatever, if I want to know if they're maximums or minimums, I should investigate those intervals. Now, what I'm about to do here is something that you will, or we will talk specifically about in a subsequent lesson here. But just to kind of lay the foundation, so it's something that you keep doing here. here's my number line. Okay, here's -3, and it doesn't exist beyond -3. Here's 2, and it doesn't exist beyond 2. And then we've got this -1 in here. Our function here is a linear function with a positive slope, so it goes up. Okay, so the derivative is positive here, it's negative here. So the derivative is going to be less than 0 on the interval -3 to -1. The derivative is positive on the interval -1 to 2, meaning that the function is decreasing on the closed interval -3 to, I'll write it like that, to -1, and increasing on the closed interval -1 to 2. Okay? So I've got that established here, which means that essentially my function is doing something like this. And I already knew this. This was no big surprise here. I already knew this. It was coming down, going up. Here's -1. Okay, actually -1. Here's -3. Here's out here 2. But the question that I don't know, okay, I don't know which is taller here. Which is my absolute max? Is it this endpoint or this endpoint? What I actually got to do here is investigate that by plugging this in. So if I plug -3 into my function, that's 2 times -3 plus 1 squared plus 3. Well, -3 plus 1 is -2, squared is 4, times 2 is 8, plus 3 is 11. If you plug in 2, this is 2 times 2 plus 1 squared plus 3. 2 plus 1 is 3, squared is 9, times 2 is 18, plus 3 is 21. So actually what I had here drawn is a little off. It's going to look more like that. Okay, so now I know that I've got right here, this one here, let's be really clear about this. This is a left-handed max. It is also the absolute max. This right here is a local, this is a local min. It is also the absolute min. What's going on here? Min. Over here, this is a right-handed max. And that's it. That's all it is. Okay? Because it's not an absolute here, and so that tells me that that's an endpoint here. So my absolute max value, because that's what the question was asking for, my absolute max value is going to be, is 21. Wow, my pencil's really falling apart here. My absolute min value is 3. Okay? And that's all this question was looking for. So I hope this lesson has given you a bit of an idea, some clarity on how we interpret intervals of increasing and decreasing, how we use them to find critical numbers, and the definitions on your max. So you've got your max and your min points, your local max, local min, requiring derivatives. You gotta be able to come up from both sides. Your right-handed or left-handed maxes and mins, meaning endpoints, and then your absolutes as well. I hope this helps. This was a tough one to go through, because I know out there's going to be some disagreements with how the choices that I've made here, but I do believe that I've been as consistent as possible with the definitions that exist.